We tend to think of seeds as passive objects waiting for water and warmth. In reality, they are actively listening to the environment above them. Germination is a high-stakes decision. If a seed sprouts while buried too deep, it will exhaust its energy reserves and suffocate before the shoot can ever reach the sun. Biological models suggest seeds track temperature and moisture levels to determine when it's safe to emerge. But moisture can saturate the ground for meters. This creates a measurement problem. A buried seed needs a way to verify it is in the shallow sweet spot of the soil before committing its limited energy to growth. Mechanical engineers at MIT identified a physical trigger for this process. They found that seeds use the explosive sound of raindrops to verify their depth. Survival hinges on the seed's ability to detect mechanical vibrations of water arriving at the surface. Because water is vastly denser than air, it transfers momentum violently. When a raindrop strikes the earth, that energy has to go somewhere. The impact of a droplet hitting a puddle generates underwater sound pressures reaching hundreds of pascals. These acoustic waves travel downward, vibrating aggressively through the soil layers as they radiate away from the point of impact. As these waves move deeper into the ground, the earth absorbs the energy, causing the acoustic pressure to dissipate. Close to the surface, the force is immense. For a seed buried within a few centimeters of the impact, the underwater sound pressure is equivalent to standing within a few meters of a jet engine in the air. This kinetic energy provides a direct link between above-ground weather events and the dormant life buried beneath the surface. To test this interaction, researchers utilized rice seeds, which naturally germinate in the submerged environments of flooded fields. Inside these cells, heavy organelles called statoliths act as internal gravity sensors. Like sand in a bottle, they settle at the bottom, pressing the membrane to indicate down. When sound waves from rain hit, the vibration shakes these statoliths off their resting spots. This mechanical displacement triggers a biological response, prompting the seed to exit its dormant state and begin the germination process. In MIT's hydrophone experiments, seeds exposed to the acoustic drumming of simulated rain sprouted 30% to 40% faster than control seeds kept in silence. Statoliths act as a mechanical switch, translating the kinetic energy of a rainstorm into accelerated biological growth. This mechanism solves the problem of depth. Only seeds in the top few centimeters of soil experience enough acoustic pressure to be shaken into an accelerated awakening. This ensures that seeds buried too deep, where they would starve before reaching the sun, do not waste their energy germinating prematurely. The discovery suggests that plants monitor a wide range of acoustic data. They may also use the vibrations of wind and rustling branches to sense changes in the world above. In agriculture, this provides a pathway for synchronized, chemical-free crop yields. Farmers could potentially use acoustic drumming to trigger germination across an entire field at once. It gives a new perspective to the idea of talking to plants. They may be more sensitive to the mechanical reality of sound than we previously realized. Uncovering this acoustic dimension redefines the sensory world of plants, showing that the sound of falling rain is a primary driver of life on Earth.